Hello, welcome to the Design Shop. I'm Ashwin, an application engineer at MAX Integrated. Today, we are going to talk about MAX40056, a bidirectional current sense amplifier suited for DC motor applications. Pulse width modulation or PWM signals are the common signals used to drive DC motors, which is used to control the torque, the velocity, and even the position. This is done by ascertaining the feedback signals from the motor itself in order to provide a responsive and an accurate system. One of the most important feedback signals ascertained from this application is the winding currents going to the motor. There are three different techniques in measuring the current going to the motor. First is the low side technique. The common procedure is to provide a current sensing element, which is usually a sense resistor, and a current sense amplifier, which is placed at the lower side of the low side switching element closer to the ground. The common mode levels at these points are closer to the ground, but there are a lot of ground variations looking into the load, which is not good. The other issue is that this technique does not indicate faults. The next technique is the high side, where a current sensing element is placed on top of the high side switching element. The issue over here is that the choice of the current sense amplifier need to be able to handle the common mode levels, which is usually the power supply, which can be about 48 volts and above. This topology can detect faults occurring at the motor. But yet the instantaneous currents feeding into the each phases of the motors are not ascertained. The third technique is the inline sensing technique, where the sense resistor and current sense amplifier is placed right after the drive in front of the motor to actually measure the inline current of each of the windings. This technique poses a lot of problems to the choice of the current sense amplifier, which basically means that the PWM levels over here are going to be from 0 to 48 volts, and the slew rates or the edge time could be in the rate of 200 volts per microsecond to 1 kilovolt per microsecond, which basically means that you need to have a very high common mode rejection from the current sense amplifier. Otherwise, your outputs from the common mode current sense amplifier is going to have erroneous signal. You want the part to settle faster during these common mode perturbations. And for this reason, we have MAX40056, which is specifically suited to work under these environments. As you can see in the slide, the inputs of MAX40056 are designed to handle high common mode levels. It has a unique architecture at the input, which rejects the PWM signals, the common mode PWM signals, providing a very high large signal common mode rejection. It also has an additional feature of overcurrent protection or fault detection. The duty cycle in DC motor applications, the duty cycle of the PWM varies at different times based on the needs, and you require the current sense amplifier to settle faster also. Now that we looked at the part, let's go to a demonstration where we show the large signal common mode rejection performance of MAX40056. As you can see on the slide, a simplified block diagram which shows a duty cycle PWM generator feeding to a driver. The output of the driver is a 0 to 48 volt PWM pulses driving an inductive load. A 0 ohm sense resistor or a short is to ensure the differential voltage across the inputs of the current sense amplifier is 0 volts, and we are actually looking at the common mode response or the common mode performance of the amplifier. Here is the MAX40056 PWM rejection board. This section over here is the duty cycle PWM generator, which generates variable duty cycle or pulse widths from about 2 microseconds to 8 microseconds. The section over here produces varying slew rates. the part device over here is MAX456 driving the inductive load. We have also chosen two competing devices driving inductive loads at the same time. This SMA output is the PWM signal. This SMA output is the output of the current sense amplifier MAX456. The SMA output over here is switched from the competitor A and B. Now let's look at the performance. As you can see, the yellow trace is the output of the PWM generator. It generates a 0 to 48 volt pulses. The board is set up to provide a 500 volt per microsecond slew rate. Ideally, for the given common mode pulses, an ideal current sense amplifier should not provide any disturbance at the output because it's a common mode signal. Now let's look at the output of each of the devices. As you can see over here, the output of MAX456, the amplitude glitches at the PWM edges are lesser than 100 millivolts, and you can see that the outputs settle faster, which makes it more responsive. Comparing it with the competing device, you can see that the amplitudes are way larger. And it does take longer to settle. Moving to competitor B, you can see the outputs aren't settled yet. And in this case, if I change my pulse width to minimum, which is 2 microseconds, you basically are seeing that the outputs of the competing device have not settled yet, but MAX456 have settled long before. Changing the slew rate of the device to about 1 kilovolt per microsecond, you see the performances are aggravated at the output, but you still see MAX456 error is still negligible. Now that we looked at the PWM common mode rejection performance, let's actually look at MAX456 being put in a real application. Let me set it up. We can take a short break and we'll meet you back later. And now we're back. This is a setup for a 3-phase BLDC motor application in constant velocity mode. This over here is industry available drive, which is driving an industry available 48 volts 3-phase motor. What we have done is we have actually added 3 MAX456 current sense amplifier inline, measuring each phases, and we are also probing the current at one of the phases, and we want to see if the output of the current sense amplifier follows the probed current. Essentially, that's what we want to do, because that provides us some information about the responsiveness of the output of the current sense amplifier and how well the output follows the probed current. Okay, now the application is up and running, and let's see. The signal over here, the yellow trace, is the phase A of the motor, and channel 2 is the output of the current sense amplifier, and channel 3 is the current probed from the same winding, which the MAX456 is measuring. And as you can see, let me go in and take a single shot. As you can see, at each PWM edge, the outputs of the current sense amplifier follows the current probed, and the output settles quickly after the PWM edge. And essentially what I would like to do is place my probed current over each other and look how close they follow. Pretty close. Okay. As you can see, MAX456 is perfectly suited for DC motor applications which require high common mode rejections in the presence of PWM signals. Thanks for joining us today at Design Shop. For more information about this device, please visit www.maximintegrated/max456. For any questions about this device, reach out to tech support@maximintegrated.com. Thank you.